Hi grade 11s, I'm so glad you could join me once again. Today we are going to be looking at grade 11's circle geometry, revising some of the important theorems that you learned in grade 11. Of course, circle geometry is extremely important for grade 12 because your final exam paper 2 will contain questions based on circle geometry. So let's have a look at the first theorem. This one is called angle at center. Many of you will recognize the statement that the angle at the center of a circle is twice the size of the angle at the circumference. Of course, it makes much more sense when we look at the different diagrams, which we are going to do just now. Importantly, in geometry, remember whenever you make any type of statement and you give, for example, x is equal to 60 degrees, and if your reason there is going to be using the angle at center theorem, then the reason you will use as angle at center is 2 times angle at circumference, and you can abbreviate the way you see on the screen. So what does this look like? So there are different types of diagrams that relate to the same theorem, that theorem being the angle at the center is 2 times the angle at the circumference. As you can see, the straightforward diagram that many of you will recognize is if the angle at the center is 2x, then if we follow this chord or this segment, but if we follow a chord that's drawn there, we'll see that that chord takes us to the center. And the same chord will take us and subtend, or subtend simply meaning it's going to make an angle that is a half the angle at the center on the circumference. Now you'll see in the second diagram, I've got a diagram that's moving around and simply showing you how the angle of center you see from the diagram that you're used to, which is the first one. You will see that this point on the circumference can move anywhere on the circumference, and as long as that angle on the circumference is subtended by the same chord that subtends the angle at the center, then we can use the same theorem, angle at center is twice the angle of the circumference, depending on where that angle moves around. Doesn't really matter. Now the one that generally learners struggle to see is the third diagram, and this is where we've got the reflex angle AOB. So we still have that we've got a chord subtending the angle. So if I join A to B, that's my chord. And you can see that AB will subtend angle C, in other words, makes an angle of C on the circumference. And if you follow that chord AB along, you get this reflex angle, this angle here, that's greater than 180 degrees, that angle there forming. And so this is the diagram that a lot of learners struggle to see and put into the same context as the other ones, but it's the same theorem. The angle at the center here, the angle at the center, which is that one, the reflex one, is twice the angle at the circumference, which is angle C. So this angle here is 2 times angle C. So say, for example, the reflex angle AOB was 200 degrees, then angle C on the circumference would be 100 degrees. Okay, using the angle at center theorem. So let's look at an example of exactly that picture, because as I say, that's the one that learners struggle with the most. So let's look at if we are given that O is the center of the circle, okay, and we are asked to find the unknown angle, which in this case is angle F. Now, if O is the center of the circle, even though we don't need the information I'm going to give you now, I always think it's a very good idea to just at the back of your mind, keep in mind the different properties and theorems that you can see. So if O is the center, I know that OJ and OK are equal because those are radii. And we also obviously will get the angle at the center being twice the angle at the circumference. But now, look at the angle we are talking about. Right? It is the reflex angle KOJ that is twice the angle F. So therefore, to set up our reasoning to find angle F, we first have to find that reflex angle JOK. How do we do that? We know that angles around a point equal 360 degrees, and we can see that the angle JOK that's inside, that's not the reflex angle, so it's your obtuse angle, that one is 120 degrees. So therefore, to find my reflex angle, I'll say it's going to be 360 degrees minus 120 degrees. And the reason there, I'm not going to put the reason in, but remember there is a reason. The reason there is angles around a point So 360 minus 120 will give me 240 degrees, which means this reflex angle is 240 degrees. Therefore, the angle on the circumference, angle F, would be equal to a half of 240 degrees. And your reason here is the angle at center theorem, as I showed you before, how you would write that reason out. So I'm not going to complete it, but I'm going to leave it as angle at center. So therefore, a half of 240 is 120 degrees. Okay, so therefore we can see that angle F, using that theorem, angle at center, that angle F is a half of the reflex angle. All right, I want to do one more on that same type of diagram. So once again, we are given that O is the center of the circle. We have to find now the angle at the center. So now we need to find out the reflex angle D. So how do we find that angle? Well, we know that angle J is equal to 100 degrees, and we see that chord KH subtends angle J and angle D. So therefore, angle D would be equal to 2 times 100 degrees, or 2 times angle J. And the reason there, again, I'm not going to put the full reason in, but you know what I mean, and you must complete that reason. Angle at center is 2 times angle at circumference. So therefore, angle D will be 2 times 100, which is 200 degrees. Okay, all right guys, so that's really the one theorem I wanted to highlight with that specific diagram, because that's the diagram that tends to give the most problems. Now, some other theorems that we learn about, we sort of just accept them as axioms. In other words, you don't need to know the proofs. Well, actually, no, they're not called theorems. These are axioms that you need to accept without knowing any proof. Those are just generally accepted ideas. So, for example, you will accept as an axiom that the radius is perpendicular to a tangent. It's not something that you're expected to prove. Now, another thing that we often use in proofs, but we aren't expected to know the proof of, is equal chords. So what the reasoning says here, or what the theorem says here, is equal chords subtend equal angles at the circumference and at the center. So if you look at my diagram, if I've got chord DC equal to chord CB, you can see those are marked with blue, meaning they're the same thing, then the angles they make, so if I follow this line DC, you see it takes me to the circumference and gives me angle A, and then BC takes me to the circumference and gives me angle E. So therefore, angle E is equal to angle A, and the reason being they're equal chords. It's one you need to remember because these often sneak into final exam questions, and learners are stuck because they cannot remember this one. All right. Similarly, if I've got chord EH equal to FG, then angle O1 is equal to angle O2 because EH and FG are equal chords. All right. Another theorem that we don't see often enough, but you need to understand and you need to be able to apply, is tangents from a common point. We don't do a lot of work on the theorem. It's almost like a statement that we just expect you to know, and so similar to an axiom, and we just want you to be able to apply this theorem when you see it in your diagrams, okay? So what does it say? It says two tangents drawn from to a circle from the same point outside the circle are equal in length. So if we have tangent EC and FC drawn from the point C, then EC is equal to FC. The reason we use whenever we come across this one is tangents from common point. Okay, all right. Let's see if we can quickly look at an example where we use these not so common theorems or axioms. Okay, so here we are told that in the diagram, AB and AE are tangents. So straight away, guys, what I like to do, like I say, when they give me information, I mark it on my diagram. If AB and AE are tangents, they're going to be equal. Why? Because tangents from a common point, okay? They tell you that BC is the diameter of the circle, and they tell you its length is x plus 7, while AC is 13 and AE is x. Now, the mere fact, or the very fact that we've already marked AE equal to AB means I can already see that the length AB is going to be x, Why? Because it's equal to AE, and those are tangents from a common point. But let's see what the question asks. It says, give reasons that angle ABC, this one is 90 degrees. So this is literally just one statement. We're just going to make a statement and leave it there. It's worth probably 1 mark in an exam. Why is angle ABC equal to 90 degrees? Well, we can see that AB was a tangent. They told us so. They also told us that BC is the diameter, and we know there's a theorem that says, or an axiom rather, because we just accept it as true, there's that axiom that says that the radius is perpendicular to the tangent. So therefore, the reason here is radius or diameter, doesn't matter which one we use, radius or diameter is perpendicular to tangent. Okay, then they say, why is AB equal to x? And we already discussed this right at the beginning. AB is equal to x because AB is equal to AE, and these are tangents from a common point. Tangents from common point. Okay. All right, guys, let's see what the next question says. It says, calculate the length of AB. Now, remember what we've used generally will help us with the questions to come in geometry, or the following questions. Calculate the length of AB. We've just shown that AB is perpendicular to BC. So that gives me a right angled triangle ABC. We also know that AB is equal to x. We've already shown that. So if I look at ABC, I've got a right angle. That means I've got the hypotenuse AC. I've got 2 shorter sides, so I can use the theorem of Pythagoras. Theorem of Pythagoras says that AC squared, which is your hypotenuse, is equal to AB squared plus BC squared. And the reason for that is theorem of Pythagoras, or you can abbreviate to Pythagoras. I can therefore rearrange that to get that AB squared is equal to AC squared, the hypotenuse squared, minus BC squared. And doing that, we will get that, and moving everything over to the one side, x squared plus x plus 7 squared, x being the length of AB, right? And x plus 7, remember, was the length of BC. So x squared plus x plus 7 squared is equal to 13 squared, and you can simplify this by squaring your binomial. So we get x squared plus 14x plus 49. I'm going to bring the 13 squared over. 13 squared is 169. Okay, so we end up with 2x squared plus 14x. 49 minus 169, that's going to give me negative 120. And then, guys, I'm going to leave it to you to simplify here. You can see the answers already given. It's just a simple matter of factorizing that quadratic trinomial. So your factors there are going to be 12 and 5. You can check it out, and you'll see that you'll get x is equal to negative 12, which we cannot accept because length cannot be negative. And so, therefore, we accept that x is equal to 5. Okay, as the only positive answer there. Guys, I think let's take a quick break, and when we come back, we're looking at more circle geometry. Back after this.